Hello everybody and welcome to our webinar today. The topic of today's webinar is high precision current transducers for range extension of power meters and power analyzers. Very welcome to our webinar today. It's a special edition today. But before we start with the webinar, just some short explanations about organizational things to allow other people to connect to our webinar. For those who have not attended our webinar until now, you have your webinar tool on your right side of your screen. Please, this is a live session. Use the chat window to ask us questions. Those questions can only see by myself and my colleagues. So no other attendee can read your name or see your message. So it's anonymous and we are going to keep it that way. So please use this possibility and ask our special guests regarding questions, and of course myself as well. We are going to answer those questions at the end of the webinar. Also, there are the handouts available for this webinar, also on your right side for download if you want to have them in digital written form. At the very end of this webinar, we are going to show two videos regarding high precision current transducers as a bonus for those who are interested in those videos, and we are going to explain the technical part behind it. But now, so let's start with this webinar, and let me introduce you with our special guest today. And it's an honor to have the know-how expert himself on the show today, and that's CEO SIGNALTEC, Horst Bezold. Horst, nice to have you on the webinar today. Hello and welcome.
Hello, thank you.
Yes, this is it from my side, Horst, and now I'm very excited about this webinar, and the stage is yours.
Good, thank you. If you think you are excited, you have to think about me. I don't know what the hell I did when I agreed on an English webinar. We don't even talk too much in English these days because, of course, we don't have that many connections to our customers. But I try to handle the expressions, and yes, I'm not an English speaker, and somehow I will deal with it. If you have questions, of course, you can write it down and send it to Ivica, and he will forward it to me. We talk about power measurement, high current transducers, and you already see here such a setup of the new PA8 deep power analyzers. This is a calibration system for power and some of the most precise current sensors available. Why do I do this seminar? Okay, Davidron is a power partner of SIGNALTEC for many years already, and recently they introduced their new power analyzers, real power analyzers with current input terminals. So more or less not a completely new player on the market, but we're a special unit with good power accuracy in the frequency range we need for inverter applications, and excellent streaming features to stream data, power data, current voltage power data in with some megahertz. So let's start. A few words about myself. My name is Horst Bezold. I'm from Nuremberg. That's where our company SIGNALTEC is, and I work in the test and measurement business since 1993, just after university, or after we say in Germany Fachhochschule, in high voltage test. And already in 1996, I joined the precision power analysis business. At that time, also an Austrian company, the company LEM Norma, who designed the first wideband power analyzer for inverter applications. You have to know that the frequency inverter has been developed in 1968 by the Danish company Danfoss, and it took almost 25 years till somebody was able to design an instrument who deals with this nasty waveform, with this very fast rise time of voltages and also distorted current values. So I joined this company in '96. So I was there at the beginning of this wideband power measurement business, mainly for industrial electric drives. In recent years, this completely changed. Our main customer segment is a automotive business. Then I founded in 2003 the company SIGNALTEC, already with a task to introduce a new technology, new old technology, because actually the technology of the current sensor is older than the inverter itself. It was developed at CERN in Switzerland in mid of the 60s, I think, but nobody of the power measurement people had a look at this special sensor. So we use special complicated or special sensors like wideband shunts, which are on potential and cause many problems. I will show you later at some slides. So we founded the SIGNALTEC and started with the Fluxgate sensor, zero flux sensor in the power analysis market, which was much smaller at that time. This was a small Danish partner, and more than 10 years ago, LEM took over this small Danish company, or better to say, just the high precision department, current sensor department from the small company. So we are now the partner of LEM. You all should LEM if you are in power electronics business. LEM is a largest company manufacturing all kind of current and voltage sensors, mainly AC, DC, Hall sensors. So I'm more or less back. In '96, I joined the company LEM Norma or LEM Instruments, and now we still we again work close together. Why do we still do this power analysis business and handle the power analysis customers? Because we can do it. LEM, of course, is a huge company and focused on delivering large quantities of sensors for different applications. But it's not really an engineering company to handle customers who design test beds. That's what we can do, and therefore we are still partner for this T&M. We are more or less the outsourced T&M department of LEM or for the LEM sensors. So yeah, we started in 2003, but soon we found out that we have to develop some own products to get rid of some problems delivered by other companies, especially with the power supplies, burn resistors, cables, and this finally led to even own digitizing systems which can be easily connected to automation surroundings, automation system like EtherCAT or CAN. Yes. So what is it different to the normal sales company? Of course, we are, as I told you, we are engineering company. We develop products ourselves to make it easier for the customer to use the sensors, and with plug and play solutions. And we don't have an in-house production. Production is done in the area of Nuremberg with some partner companies. At some partner companies, we do the development here together also with a partner, the company Redcur, which is situated here in our office. And of course, we have to test everything. So we have built up a nice lab. In my point of view, all for measuring amplitude, accuracy, and phase shift, and this in a wide amplitude and frequency range to see how the stuff performs, what we develop. We have to measure each power supply for the sensor. How much noise does it create? How can we filter this? How can we improve the quality of the output signal of the sensors? And of course, we need the lab for adjustment. Since we make active amplifiers, they need to be adjusted down to the ppm range for supporting. Of course, if we get defective or customers think they have a defective sensor or it's not accurate enough, we can easily test it in our lab. And the most important thing for this wide current large power simulation lab is a specification of the AC specification of the transducers in our data sheet. This is actually done at SIGNALTEC and not at LEM. LEM provides DC specification, but also AC phase shift, amplitude accuracy, versus frequency over the whole frequency range is done here in our lab. So we can generate DC up to 1000 amps, AC up to 2000 amps. Of course, we can use with some turns, we can test sensors up to 5 kilo amps in the DC range, in the low frequent range. But for the small signal analysis, for the wideband analysis and of bandwidth analysis, we have analog amplifiers to create currents up to 20 amps, up to 100 kilohertz. And for the small modules, even the burden resistors, active passive burden resistors, we can simulate power into the megahertz range. Yes, what are we talking about? What is the agenda? Of course, everything is about power. We talk about efficiency and losses. Then about the basics of power and how is electric power defined, different current sensor technologies, and our high precision Fluxgate transducer, and finally about the products we have in our range, what we deliver with the sensors as complete systems to our customers. Yeah, when we talk about the business and the application for the high precision sensors, there is of course a huge OEM business, when or not huge, but a reasonable sized OEM business, which is covered by LEM, delivering sensors for control technologies, especially here in battery systems. This is a battery system, a battery simulator, a load, a source, which is actually representing the battery in a test bed, not a small battery of a combustion, a starter battery of a combustion car, but of an electric car, some large cabinets to simulate this battery in the test bed. There's another OEM business. It's the medical business, magnet resonance imaging. You need one sensor for each direction to control and measure the magnetic field in for magnet resonance imaging. In a very small market in physics, that's where the sensor comes from, developed at CERN to control the magnetic field at particle acceleration. Of course, you need a very stable magnetic field to control this stable or to generate this stable magnetic field. You need large magnets and very stable power supplies, and these power supplies have to be controlled somehow. And for this, the DCCT, the Fluxgate transducer, has been developed. Okay, and then the business we are talking about, it's motor test beds, and this, as I told you already, changed a lot when we made where the business in the past was industrial drive, so three-phase input in inverter, three-phase sinus signals from the grid into inverter, and then the output variable output frequency to drive large motors in traction or windmills, industrial drive. But yeah, this business dropped a lot, and meanwhile meanwhile, most of the business is development and test bed, end of line test in the automotive industry. Yeah, e-drive testing for e-mobiles and hybrid cars. In such a system, you have your battery simulator, of course. Then you have your devices under test. The inverter has some losses. The motor has some losses. And of course, the core element, it's a power analyzer. In this image, it's a PA7. That is a smaller Debitron unit, or the unit which has been launched already 2 years ago, as far as I remember. Which is able to measure 1,000 volts or even more than 1,000 volts in the power circuit directly, but like all power analyzer, like all instruments, it's able to measure just a few milliamps or a few amps. You cannot connect 1,000 amps or even more, 1,500 amps, what we see nowadays in our automotive business, directly to an instrument. You have to use a sensor, and you have to use a sensor which is equal precise, best case much more precise than the instrument itself, that you can still guarantee that you measure your electric power with a very high accuracy. You have to measure the DC at the input of the inverter. Then we have a very distorted signal, very distorted voltage at the output, also distorted current at the output, synchronously, very important. Even this DC voltage is not completely stable, and of course very distorted, unstable, and stable output. But to measure the losses and or calculate efficiencies, you have to synchronize every value down to in the nanosecond range. And of course, we are interested in the losses of the electric machine, and the electric machine, the output of the electric machine has to be measured with a torque speed sensor, torque speed shaft, which is shown here. Then we have a lobe machine, and if it's a good test bed design, we just push the generated power with another inverter back or rectifier back into the DC link circuit. Okay, that's the application, and here again you see the setup of the test system and how to calculate losses. Of course, to calculate all the losses of the inverter, I take the input power and subtract the output power, and the difference between input and output power gets me the losses. This calculation gets me the losses of the inverter. The same, of course, with the electric motor. You measure the three-phase input power and mechanical output power, and then you get the motor, and so you can add the losses for the total losses. Easy calculation. The calculation is easy, but the whole thing, or since we have to calculate the losses, that we cannot measure the losses, it makes this efficiency calculation much more complicated and much less precise. We cannot measure losses directly. We have reasonably, or we have instruments with a very good accuracy, but we can only measure the input in at a normal resistor. I measure the voltage and I measure so I know the losses of this resistor is a measured value with measured with high precision. At inverters and motors, we have to calculate the losses from two different power values, and that makes it very complicated. It's a differential measurement. The losses can't be measured directly. And the second problem of this setup is that the efficiencies are rather high, so which makes it even worse. So we talk about efficiency of motors between 90–95%, but at inverters, so 98% or even 99%. And if you have to calculate these losses with high precision, you have to measure with even much higher precision. This is, for example, a calculation of the motor losses. We use a motor with 95% efficiency, push 100 watts into the system, and we measure with a total power accuracy of 0.1%. What happens in worst case? In worst case, of course, we measure with 0.1%, where our actual losses are 5 watts. We measure 100 watts in the inputs, plus minus 0.1 watt, and 95 at the output, plus minus 0.1 watt. So our uncertainty is, so we get at the output something between 4.8 and 4.8 and 5.2 watts. Our uncertainty of this measurement is 4%, almost 4%, but we measure with 0.1%. And this is a problem of, and why this discussion went on for many years, that it is not possible to measure inverter losses or to calculate inverter losses. We really had convinced the people that we can do it, and sometimes we got more than 100% in the output when we had huge disturbances, especially with the shunt measurement. But this is the main problem, and you can imagine that this is a 95% efficiency. If you have a 99% efficiency, this measurement uncertainty due to this differential calculation increases to 20%. This is the main problem of efficiency measurement. One of the problems, especially for the motors, for the motor efficiency measurement, that we have meanwhile very precise instruments and extremely precise current sensors, but the torque speed shift is it's good, or they improve. This one is probably the most precise available in the market from HBM, but it's much less accurate than our electrical measurement. So we can improve the situation a little bit with a back-to-back setup. This came up in recent years, and when you talk to the motor developers, they say the motor in driving mode has the same losses like the same motor in generating mode. So a possibility for a more precise setup could be this so-called back-to-back inverter, where we use one as a motor, the other one as a generator, identical motors, of course. And in case if both have an efficiency, each of 95%, we get a higher higher losses, and this makes the measurement and the differential calculation much easier. Yeah, of course you need no more electrical channel, but you get rid of the mechanical problem, or of the problem of the mechanical inaccuracy of the torque speed shift. Okay, basics of power measurement. Yeah, I know that the signals we deal with are very distorted, but to show the problems of power measurement, I show it here with sinusoidal waveforms. We see a green voltage. We have a red current which is shifted in phase. This is the natural phase shift of our load. Normally we deal with inductive loads, so the current follows the voltage. This must be a phase shift on, I think, around 60 degrees. And voltage following current, and when we want to get the AC power, we have to calculate the power waveform and average it over a certain time, certain period, certain update rate. And in this waveform, in this formula, you see all the problems you can have with your power measurement system. First of all, you have to measure, of course, with high precision. I think the Davidron system samples with 18-bit and also has reasonable analog accuracy to measure electrical signal. And we have a very precise sensor. So we have the amplitude accuracy is very high. We will get very accurate sample values for voltage and current, and therefore we can calculate a very precise power waveform. The next important, or the second important item is that we have to we set the sample exactly at the same time. If we have a phase shift of our instrument or our sensor, then of course we shift the current. Let's say we have a phase shift in our current sensor. We shift the current waveform to the left or to the right side, and this will also result in a wrong power waveform, because then we shift the power waveform up or down. This is what we call the phase angle error. This must be as low as possible. Amplitude, phase, and the third point is the averaging over exactly one or several cycle times. You have to synchronize from zero crossing to zero crossing, but when you see your inverter voltage, there's no zero crossing available. You have to do a lot of filtering. In German, we say to this synchronization, we say Abbruchfehler, and I try to Google, and you get the direct translation with this abort error. I don't know whether this is the right expression. Sounds strange for me, but the problem is, of course, if I don't catch the zero crossing, I sample in my averaging period too many or too less of the sample values, which will result in a power error. Okay, here again our power system, current and voltage. Load is inductive, electric motor, and this causes a phase shift in current and voltage. At the beginning, there's phase shift 0, power factor 1, and you see with increasing of the phase angle, the power waveform will move down, and finally we have just negative power. The active power is the arithmetic mean of this positive and negative section or area, and the problem of power measurement at different power factors, it's much easier at power factor 1 or -1 than it is at power factor 0. I can stop the waveform here. Power factor 0 is when we have as many positive components, power components, and negative sections. So power is 0, and that's at power 0. So everything what we show at the instrument is the error is infinite, because I will show you here. Let's make a calculation. We use power system with an angle error of 0.1 degree, and use the same system and the same power measurement system to measure power at 2 different power factors. The first section here is at power factor 1, current and voltage in phase, and the second one is at power factor 0.1. Let's say it's an electric motor in the no load case. You can easily go down to 0.1 power factor, 100 volts, 1 watt. And let's do the calculation. We have this 0.1 degree phase error, and at section 1, we shift due to our phase error the actual natural phase shift from 0 degree to 0.1 degree, and then we calculate the cosinus of 0.1 degree. It's close to 0.1, so you compare it with 0.1. The 0.1, So you see at power factor 1, even a larger phase shift of 1.1 degree won't cause much of a power error. It's at the ppm range. Then we do the same calculation as the power factor of 0.1, which is a natural phase shift or phase shift given by the load of 84.261 degree. Then, due to our phase error, we shift the current waveform from 84.261 to 84.361 and do the coordinates calculation. Then we get 0.0983, which differs from the actual 0.1 by 1.7%. You see this phase angle influence is depending very much on the power factor, and the closer you come to 0, the larger becomes a problem of the phase shift. If you're, yeah. So, and of course, it's a linear. The problem increases linear with the frequency. If you have 0.1 degree phase shift at 50 hertz, then you will have 1 degree at 500 hertz and 2 degree at 1 kilohertz. And our frequency, fundamental frequencies in automotive business go up to 2 or 2.5 kilohertz. What frequency do we have to deal with in drive technology? Or of course, you see here's a line voltage. You will know it probably. The line voltage and the following almost sinusoidal current. What frequency do we have precisely to analyze? It's first of all the DC. The DC in the battery circuit or DC link circuit. Then, yeah, it's more or less from the past. In traction, we had to measure very low frequencies. In automotive business, the fundamental frequency goes up to 2.5 kilohertz. This is already a task and or a challenge. And then we have switching frequencies right now with our older semiconductors up to 20 kilohertz. New silicon carbide semiconductors are much faster, so I expect if these components get cheaper, that the switching frequencies rise a lot, up to maybe 100 or even more than 100 kilohertz, which is a huge problem for measurement. I will show you later. And we have some megahertz, many megahertz in this voltage ramp. And if you ask me if I can provide you a sensor which measures with highest precision, even at lower power factor at some megahertz, I cannot. And probably if you ask Davidron whether their power meter is extremely precise at some megahertz, they have to deny it. It's more or less not possible. But since the inductance leads to almost sinusoidal waveform of the current, we don't need to measure some megahertz in power. We have to be sure that we measure the fundamental frequency with highest precision, and then we measure the losses, the switching losses, with a reasonable accuracy. But we don't care about any megahertz signals. This is a simulation, for example. This is a rectangular voltage which contains more or less all frequencies, and a sinus current generated from a frequency, two-channel frequency generator, and then we see the voltage and the current spectrum from these signals. So even the sinus seems to be a little bit bent. It's a logarithmic scale, so you see this third harmonics in even a little bit of a third harmonics in the current. But okay, in our application, due to the impedance, even at this terrible voltage signal, the current is almost sinusoidal. And one thing is important, just harmonics or frequency components of same order or frequency of voltage and current result in active power. power is calculated, or the frequency components are calculated voltage, efficiency value times current efficiency times the cosinus of the phase angle BP voltage and current. But if current is zero, or better, if the frequency component of the curve is zero, so it wouldn't result in any power. So this makes life much easier, and that's what I say. Why I say at least 95, normally 99% of the losses of active power, not of the losses, 99% of the active power is fundamental frequency power. This means we really have to measure with highest precision. We have to optimize everything on the fundamental frequency range, and of course need to measure with reasonable accuracy the switching losses and the switching frequency at 20 kilohertz, but we don't have to measure any megahertz in current or in power. Yeah, it could be proven at the inverter. This is the inverter voltage, but not the line voltage. This is the phase voltage. It's not. It looks different, of course. We measure against an artificial star point or virtual star point, which is I think it's calculated in the Davidron unit. And again, our phase current, phase voltage, phase current, and phase voltage times phase current times phase shift would result in active power. But of course, with you have to do this calculation for each frequency component. Not so important here. You see our wideband. To be honest, it doesn't look always this terrible, because we have the same rise time of the voltage, but only a few milliamps. That's the Davidron demo inverter. It provides a few hundred milliamps. The waveforms look much better if we measure a few hundred amps. So it's very distorted. Looks terrible, but it shows that the wideband voltage contains lots of higher frequency components. So the difference between the wideband voltage value and the fundamental voltage value, it difference with 11%. But the current, the difference between the wideband current and the wideband and the fundamental current is only very low. It's very sinusoidal. And this result, or the result is that also the power, the fundamental power, or also the wideband power, does not differ much from the fundamental power. So most of the frequency, or it's very important to measure fundamental values. Higher frequent values in power are not so important anymore. Yeah, that's more or less a story from the past, because when I told you, okay, we had the first power analyzer in the beginning of the 90s, we still haven't had the right sensor. It was a digitizing system with high precision at the times already, but we hadn't had this precise current sensor. So what has been done? We developed, or Norma developed, its own shunt resistor. A coaxial shunt resistor, of course, is a very wide band sensor with a good linearity and in the low phase shifts. This, for example, is a 1000 amp sensor that we used in the past for power measurement. But this creates many problems. Of course, you cannot get out a huge voltage, from the sensor. It's a 1000 amp sensor. If you would expect an output voltage of 1 volt, it would mean 1000 amps times 1 volt voltage drop. We would have 1 kilowatt losses. It would just burn or melt or probably explode. So there's the resistance materials was very thick, and the voltage drop therefore very, very low. We talked about some microohms and some millivolts of output signal at 1000 amps. When we have a look at our inverter signals, again, we have 500 volts in the DC link. We have voltage drive times up to this point is up to 10 kV per microsecond, and a current which should be easy to measure because it's almost a sinus. The problem is when we put the shunt into the system and connect it via a coaxial cable to the instrument, then we get huge disturbances due to this rise time of the voltage. The current through the shunt is sinusoidal, but the resistor jumps up and down with 10 kilovolts per microseconds, and also this voltage drop of a few millivolts jumps up and down in the megahertz range. Then we lead this to our instrument input channel, and it's very clear what happens. Due to the capacitance of low capacitance against ground of the instrument and the rise time of the voltage, we get a capacitive current against ground. It's a so-called common mode current or common mode error, common mode disturbance. You cannot do much against this current. You can, there could be additional shielding. It's very complicated, but when you see that nowadays we talk about 10 kV from 10 kilovolts per microsecond, but in the near future, maybe with silicon carbide, we talk about 70 kilovolts per microsecond, that this current increases during this rise time to 1 amp to 7 amp. And this 7 amp, of course, cause a voltage drop at the input lead to the amplifier. It will result, and it has result in huge disturbances. And that was actually the revolution to improve or to make measurements at inverter signals easier. What do? We have a sensor, or we use a sensor which is even much more precise than a shunt, with a much lower temperature influence and a good accuracy, and it's galvanic separated. The low capacitance to the instrument is just 1 or 2 picofarads. There's not much current flowing to ground. Yeah, what are common sensors? I think I know at least 20 different technologies to measure current. The standard sensor is just the AC transformer. You should know it from AC clamps or from the measurement in the AC grid. It's just a transformer when you induce a primary current via a core, AC core, into a secondary winding. Of course, it cannot measure DC. You can magnetize the core with a DC, but you cannot induce into a secondary winding. It has a low bandwidth. It also has not at the highest accuracy because, of course, you have to magnetize the core. The linearity of the core will influence the result, and also due to the inductance, the bandwidth is not very high. Medium accuracy, and the accuracy is very, very depending on the output resistance of the secondary winding. And of course, due to the bandwidth, it's not used in power measurement, power analysis. Then we have our first Hall sensor, or our cheapest way to measure DC currents. It's an Hall element. You have an iron core, and as I told you, you can magnetize the iron core with a DC. You just cannot induce into a secondary winding. But instead of a secondary winding, the element here is a Hall sensor element, and the Hall sensor element gives out proportional voltage, or voltage which is proportional to the surrounding magnetic field. It's still not very precise or very linear, because we have to magnetize the whole core, the core, and so therefore the core linearity will make it rather unprecise. It is a cheap transducer. It's used in inverters, to control inverters, to measure the to control frequency inverters. And it can measure AC and DC with an accuracy of around 1% of range. The accuracy and the bandwidth can be improved if we try to keep this core in zero flux. It's the first zero flux transducer. We talk about zero flux transducers today, or flux transducers today, but this is already a kind of zero flux transducer. We use the output voltage, amplify it, and lead a secondary current, magnetize the current, magnetize the core in opposite direction with a secondary current, so it keeps the core in almost in zero flux. So the linearity of the core is not so important anymore, and this will increase the accuracy a lot. Then we talk about 0.3% of range, AC plus DC, higher bandwidth, because the core is in zero flux, but it's still not precise enough, and it's still very sensitive against electric fields and magnetic fields, external fields, because of this open air gap with our Hall sensor element. For power analysis, we need a galvanic separation, but also high bandwidth, high accuracy. So these sensors are not usable for this or efficiency analysis. And this leads finally to this Fluxgate sensor, which has been developed in the 60s at CERN, as far as I know, but hasn't been used almost till year 2000 for power analysis. Haven't been optimized for AC, but they can measure AC plus DC, and they are extremely precise and have high linearity and low temperature coefficient. This is the principle. Nobody will manufacture a transducer like this because of several reasons, but the Hall sensor element that you saw in this air gap in the Hall element, or in the Hall sensor, in the Hall based sensor transducer, is replaced here with an inductor. And the inductor has a characteristic: if you apply a oscillating rectangular voltage and magnetize the core up to the saturation, it will result in a very symmetrical magnetization current, where the positive peak and the negative peak is exactly equal. And when you apply an additional DC to this core, this will shift, and you will see an asymmetry, and this is a ppm precise measurement of the DC current. So you get out a very, very precise DC value. You can out of the sensor, it will amplify it, and of course and the core will magnetize with the signal in opposite direction. So we have again a zero flux sensor, and that's a good DC sensor, perfect DC sensor with ppm accuracy. The problem, and this is the reason why nobody uses this sensor actually, that we have this oscillating circuit at the same core like our compensation winding, which already is contains or leads the output current. This is the output current or the output voltage via this burden resistor. But of course, this oscillating signal of some 100 Hertz, some kilohertz, will inject some disturbances in our output signal. You see the blue waveform is the noise caused by our oscillator. Yeah, and that is actually the sensor, how it has been manufactured in the past 20 years, I think. And also our old IT series, you know, the blue sensors use this principle when we just take a second inductor, same cause, same winding, and magnetize it in the opposite direction. So it's less, the precision of the sensor is less an electronic problem. It's a mechanical problem. How equal do I get these both cores? So we still evaluate the output of our DC sensor, of our DC core. We add an AC signal. It's just a transformer winding, amplify everything and put it, magnetize the core in opposite direction. And so we have here a very precise AC plus DC output current. And due to this compensation of the second inductor, we get a much lower noise at the output. This is the red. We talk about the remaining reinjection. How precise can we get this both, or manufacture this both cores? And this is the remaining reinjection of the IT technology. And since 2 years, we have even something new which improves the situation more. It's a LEM IN series. It's a wonderful idea. Again, we use just one inductor. But the noise created by this inductor is learned during the production process. And then we have a DSP, and the noise of the inductor is programmed in this DSP, and then we have an electronic compensation. We have an arbitrary generator in this DSP and an amplifier at the output, so we can magnetize the core with this noise waveform in exactly the opposite direction. So this is an electronic ripple compensation circuit. Just one core needed in electronic compensation. So it's the newest development, and this reduces the noise even more. So you see the green waveform, it's a remaining reinjection of the IN series. And this is a LEM patented, it's a LEM patent, more precise, less noisy, the new IN series. What does this mean for our power measurement applications? See the old noisy signal, the uncompensated noise core, then the IT series with this red peaks, and the new IN series with almost completely compensated noise disturbances. It doesn't mean anything for us. It's not important for power measurement because, as I told you, only the equal frequencies of current and voltage generate a power frequency or will result in power. And therefore, if we have we have noise in the current, but we don't have the same frequency in our voltage signal, it won't influence our power accuracy at all. So for us, I wouldn't say it's nonsense because it's always nice to see smooth waveforms at the output, or only the waveforms that we expect by our load and not disturbances for our sensor. But regarding power, it does not influence the accuracy. But what for me is the advantage of the new sensor, it's an electronic circuit, that we don't have many analog components. Everything is programmed in this digital signal processor, which increases analog accuracy a lot. And that's what I measured. So due to the microprocessor, we get a much higher accuracy. We can even program the So, oh, where are we? Here. We can even program and compensate the DC error of core of the core, and very stable with a digital circuit, which is what is always better than working with an analog potentiometer, of course. Yeah, so you see the new specification. We are even working on better specification, but we are now in the range of 10 ppm. 10 ppm of uncertainty doesn't mean that we are 10 ppm. We measure with 10 ppm, but the uncertainty in worst case, it could be that has this sensor has an error of 11.5 ppm. Temperature coefficient is very low, below 1 ppm per Kelvin, and also the bandwidth is very high. The first three sensors that we had, the first one was the IN2000, then the IN1000, and now the IN500, and I think the smaller one will follow soon, early next year. Yeah, we can test here. We cannot calibrate because to be a calibration lab, you have to need an accreditation from the national labs, from the PDB or METAS. Or if we want to prove the accuracy, we have to go to a calibration lab, and this was one of our first IN2000 sensors that we sent to the calibration lab for calibration, and you see precise results, almost zero in DC amplitude and almost zero in AC amplitude, and also the phase angle in the minute range or below 1 minute. 60 minutes is 1 degree, so it's also very small. But I don't rely so much about this because the problem of the calibration right now is that the uncertainty of the specification of the new IN series is so precise that the commercial calibration labs cannot really calibrate it, because the uncertainty of the calibration lab, of the commercial lab, especially of the commercial lab, is higher than the specification of the sensor. So we will get this value, but everything is marked okay. We measure this, but we cannot guarantee it because the sensor is more precise than our lab. Of course, the national calibration labs like PDB in Germany or METAS in Switzerland, they can do this, but it's important, and you have to wait a lot till you get the sensor back. Okay, here's the setup. Here's the setup with a PA7, so the first Davidron unit, and with a very, very precise calibrator. We're not a calibration lab, but we have a few calibrators for AC and DC. This is a calibrator up to 60 amps and 1000 volts. You can create 1000 volts, you can create 60 amps, and you can shift it in phase. And you can rely on the display of the calibrators that these values are precise. So we use the IN1000 connected to the PA8 current input, PA7 current input. So the output current is directly measured from the PA7, and also the transducers supplied by internal power supply of the PA7 instrument. PA7 and PA8 have own transducer power supply, which have advantages and also disadvantages. I might tell you something about it. And so we measure here, and we go down to a much lower power factor, not 0.1, which is already not as easy to measure as 1, but we go down to 1/1000 to 0.01 power factor, which is equal to a phase shift of 89.943 degree, measured created with a calibrator measured with a PA7 plus a sensor. We create here 50 amps, I think. It's a calibrator which works up to 60 amps, but we create only 50 amps, and we use 2 turns through the sensor. 50 amps times 2 is 100 amps. We measure 100 amps. The result is 100 volt, 100 amps, and especially for the phase shift, we really measure the 89.943 degree and the power factor of 0.001. So, yeah, very precise even at lowest power factor. Yeah, that was a low frequency calibration test, calibrator test, and here one setup with a new PA8 already, and the newest sensor we have, the IN500, and this test is the proof of amplitude and phase accuracy over a wide frequency range. Oh, it will last a little bit longer. I just show you the test of wideband amplitude phase test. We don't do it with a PA. Of course, it's a good power meter for the reasonable frequency range for inverter applications. But for if you would like to measure, to do a components analysis in the 100 kilohertz or some 100 kilohertz frequency range, you need a very wide bandwidth power oscilloscope. But we create here an electric power. We simulate electric power with a function generator and a current amplifier. So we can generate here 2 voltages with variable frequency and phase shift, and the first one is used for voltage measurement. The second one is amplified to a current, and with some loop we can compare the output of the sensor against the internal burden resistor, which should be precise in the PA power analyzer. It was just a 2 amp measurement, 2 amp measured with the 2 amp internal shunt, 2 amp times 5 turns through the transducer results in 10 amp windings, and you see at 10 kilohertz fundamental frequency with different, and only 1% of the transducer range, we different just in 4 milliamps at 10 kilohertz. At higher frequency, as I told you, I need a components analyzer, and so I measured with 20 amps. With 20 amps, the sensor up to 100 kilohertz with a very low current drop, or with a very low inaccuracy of around 0.1%, and extremely low phase shift at 100 kilohertz of 0.073 degree, and at lower current even up to the 500 kilohertz. Right? This is, yeah, the most precise sensor right now we have for power measurement. What do we offer? As I told you, besides the sensors from LEM, we manufacture our own transducer power supplies and cables, and see that everything is providing good output, good quality of the output signal, good less noisy power supplies. And this is a plug and play solution. A rack you can connect up to 6 sensors, and you get directly the output current to connect it to the power analyzer. And we also have older, larger sensors for industrial drive up to 5 kiloamps or 24 kiloamps. PA7, PA8 have own power supplies, but this is our solution. More and more of the power meter manufacturers have own internal power supplies, which has, of course, the advantage of an easy connection of the sensor to the power meter. It also has some disadvantages. You bring noise in with the power supplies, you bring additional noise inside of the instrument, and you also bring additional heat and temperature increase inside of the power meter, which makes things normally more complicated to get really high precise results. So we have own power supplies for all kind of instruments and data acquisition systems. It's a single channel system and a multi-channel system. And the difference from us to all the other manufacturers of transducer power supplies that we have all a galvanic separation between each channel. So less noise or less disturbing from one channel to the other, and we also provide the sensor readout. You can check the sensor status, and if the power supply is switched on or if the transducer is an overload, and you can read out the sensor data and switch off your primary current if you see a disturbance of the sensor. You get the output current here with a D-sub. You connect the sensor with different cables, also different diameters. We have to verify that also our larger sensors, the 2000 amp sensor, have to work with our cables, even if we provide a 30 or 40 meter connection cable. And it's connected to the D-sub, and it's a 4 millimeter safety plug. You get out the output current. And we have another power supply per each in each channel, and this is for the active output modules if we need to amplify the output current to a higher output voltage. Ibiza, how about time? Is it a problem to make 10 minutes longer, or should we?
No, I think it should not be a problem. It looks really good. So it was very interesting until now, and I think the last couple of
we have a couple of slides. So
yeah,
stay
I think
tuned.
3 slides are left. Yeah.
Okay.
Sounds good. Yeah.
Okay. So it will only last 5 minutes more, I think.
Yes.
Okay, our burden solutions, our burden resistors. We have high precision burden resistors, which can be easily plugged on the back panel of the MCDS and TPS system, and these are high precision. I'm only too far. These are high precision passive burden resistors, values available from 1 ohm to 50 amps with a reasonable high tolerance, and especially a very, very low phase angle error and a low temperature coefficient. This is the test result of the measurement of on 1 ohm passive burden resistor, also again with our power setup, with a power simulation, but in this case in up to the megahertz range with only a low current. It's a 1 amp shunt, and it's tested with 500 milliamps, and you see with this high frequent instrument. High frequent instrument that we measure the current of 500 milliamps with a deviation of maybe 1 milliamp, and nobody can tell you who is right, our burden resistor or the reference instrument. But we are here at 750 kilohertz, and the phase shift, the phase difference between two measurements is just below 1 degree. It's 990 milledegrees. For some instruments, for some data acquisition analyzers, or better to say digitizing systems, we have to provide output amplifier. You must note that there are some systems available which have only the lower, which offers a lowest range of plus minus 10 volts peak, And our current sensors normally cannot drive that high output voltage. The power supply voltage of the sensor is 15 volts. We have a huge voltage drop on the compensation winding, so we cannot get 10 or 15 volt out of the sensor, of course. And so we use the passive shunt, and we have designed a high precision output amplifier to amplify the normal output voltage of 1 volt to 7 volts. Why 7 volts? 7 volts is the reason our sensors are specified with RMS range. So the 1000 amp sensor is a 1000 amps RMS sensor, and so we give out 7 volt RMS at nominal transducer range, which is equal to 9.9 volts peak or 10 volt peak, which fits exactly to some data acquisition systems. Also good tolerance, the adjustment, I think I can adjust it even to some ppm. And the angle error is not as good as the angle error of the passive shunt, but still very precise, up to 10 kilohertz, and also reasonable high accuracy at 100 kilohertz. The phase shift is below 1 degree at 100 kilohertz. Now, the latest developments, it's digitizing output, digital output of the sensors, also with highest accuracy. The demand comes from the testbed manufacturer, who need to measure and to control the DC of the battery simulations, the DC current of the battery simulation, and don't want to bother with burden resistors, with transducer power supplies and additional digitizers. So we designed a system that integrates the sensor into EtherCAT, in the system, automation system. Yeah, it's around 1.5 or 2 years old. Power supply is included. You just connect the sensor, you connect your EtherCAT system, and get the current measured with a very high accuracy. It's a DIN rail design for test cabinets, and but it's dedicated for DC measurement. We don't do AC synchronization. It's just a very high resolution measurement, high precise DC measurement, but with very short cycle times, down to 100 microseconds, and very high accuracy. That's the DC calibrator and the digitized system of a tool with digitized output of the ECT, EtherCAT converter, of a 200 amp transducer. And this system will be followed soon by the next development, which will be launched probably next month. It's a power lens, and the power lens is it's similar to the EtherCAT. It includes the EtherCAT system, but it expands the system to voltage measurement. So the system is also a DIN rail design, but it will have inputs for the current transducers and for a voltage measurement up to 2000 volts, up to the 1000 volts, to measure the output voltage of the battery simulator as well. And besides the EtherCAT output, we have another another output to measure or to connect the transducer directly to a CAN bus. Okay, available, or the first test will be done in October, available end of this year, early next year. So I think I've finished with the presentation. I hope you did understand my English. And you finally got, or the problems of power measurement in inverter drives. I would give back to Ivica and Davidron, but if you have time, and I provided 3 videos in our lab to show the accuracy and shows us some tests with the PA8 and the sensors. Ivica, was denkst du?
Yes, Horst, thank you very much. Your English was perfect. Really, thank you so much. And it was really understandable. I'm always amazed how easy you can explain those very complex measurements. So it was really good. Yes, I have. Yeah.
Still jemand hier are still listeners here and okay.
Yes.
Okay.
Yes, definitely. We still have listeners here. So that's the webinar, and as I said, we're going to have a bonus at the end of the webinar. We're going to show 2 or 3 videos. If you're still interested, stay with us. And Horst is going to explain what he did film and to show you some measurements. And yeah, Horst, if you still want to,
okay.
you're free to continue.
Okay.
Of course. Yeah.
Okay. I start. The first one is I told you we have to test everything, and this is the first test, the test of a power simulation with 2000 amp transducers. We simulate power with a synchronized voltage calibrator and with a switch mode power supply current source, which is synchronized.
Mm-hmm.
It's not extreme. It's not as stable as a calibrator, but since we measure or with a multi-channel system, with a multi-channel power analyzer, with a PA8, it's a synchronized measurement. You will see the precision. We have 2000 amp sensors, and the difference between both 1000 amp sensors is just the cable length. Here you see the back panel of the PA8, and you see that the PA8 is able to power the sensor. That's the adapter for the current transducers, and the output of the current transducer is measured in channel 1. It's a 1 amp shunt, and in channel 2 it's also a 1 amp shunt of PA8. Yeah, same sensors should show the same results, of course, and as I told you, we expect that we are quite precise, but the difference is how to show the influence of the cable length. So that's our office, by the way, in the kitchen. And you see the first sensor is connected with a short 2.5 meter cables, and the second sensor with a 30 meter cables, which should influence somehow, if you even think about how fast the current travels inside a cable with 2000 kilometers per second. It should influence the accuracy somehow. And you see of our power simulation, the third line, the blue line, it's the sensor with the 2.5 meter cables, and the red line is the sensor with connected with the 30 meters. And that is really interesting because it's interesting. We have 1000 volts AC. We have 600 amps AC. We are at a high power factor. So the phase shift caused by the cable shouldn't influence power that much. But you see here we measure almost down with an accuracy almost down to the milliamp, to some milliamp the current, and also the phase shift is very low. Measurement: 2.5 meter cables, 30 meter cables, both frequency and the deviation between both current outputs and the deviation of the current between both powers, and the deviation between both current between both angles, phase angles. Yeah, we do this at 1000 amps, which is full range of the sensor, of course, and I think I can move forward. Then I change the power factor, which makes it of course more complicated. When we go even down below 0.1, which increases the problem of a phase shift of a long cable, of a capacitance of a cable, for example, and even at 1000 amps in power factor 0.1, you see there's no difference visible in the phase shift, or in almost no difference visible in amplitude or power. And then of course we go at this lower power factor again down with the current. So cable influence, or more or less not visible.
Mm-hmm.
Second video, it's just the introduction for the third one actually. Again, power simulation with some transducers, and this shows that we can add the output current of two sensors in one power meter channel. You see here 2I in 500 parallel and 1I in 1000. In these sensors measure in parallel, each around 500 amps, depending on the symmetry of this cable. Probably it's not exactly that each one gets 500 amps, maybe one 190, the other one 510. But we can summarize both output currents at the input of a power meter. So we summarize, it's an analog summarization of the output current at the power analyzer. It's this time I powered the sensors with our power supply, and the reason is not that it's not working with a Davidron, with a PA8. The reason was I haven't got enough current adapters to power three transducers from the PA8. I just had two, and I needed three. So 3-channel measurement, two times 500 amps, 1 times 1000 amps, but a summarization of the output current in one shunt. And just to show how precise the sensors are, and you won't see any difference, not even at power factor 0.1. Why do I show you this? This will lead us to the third video, and of course this is especially interesting for our large current sensor. Our largest current sensor for AC measurement is a 5 kiloamp sensor, but meanwhile we have application in industry which demand 10 kiloamps, and so we tell the customers, yes, use two 5 kiloamp sensors in parallel, and then you can measure 10 kiloamps, because we don't have a good AC sensor for above 5 kiloamps. We won't develop one, I'm sure, because the market is very slow. Yeah, parallel transducers in parallel.
Mm-hmm.
And the third one is also transducers in parallel, but this time anti-parallel. This is where we create 1000 amps. We have 2000 amp sensors, but we do not add those currents. We will subtract both currents. I do this with the highest precise DC meters we have in the labs. It's 8.5 digits multimeters with a few ppm accuracy. Two transducers. Transducer one measured with one system, one DC power DC multimeter. The second transducer with a second one, but we have a third, less precise, which adds both current but in the opposite direction, anti-parallel connection, which should give, in best case, the result. If we are really precise, this must be 0, of course. Mm-hmm. And then I try to shorten it a little bit. We are at 9 amps precise. Both difference between both sensors is in the milliamp range. then we go up to 200 amps. The difference between those sensors is below 1 milliamps. So the ratio of the sensor 1,500 is already programmed in the instrument. So we measure with an accuracy of less than or with a difference of less than 1 milliamp. Let's go up to 1000 amps. We are here at 1000 amps. 1000 amps with transducer 1, with transducer 2, and the difference between both transducers is around 0.6 milliamp. This is shows me that the sensors are specified with maybe 10 ppm, but the actual accuracy is rather in the range of 1 to 3 ppm. So that's just 3 videos to show the accuracy in our lab. This is really the end of the presentation. I thank you for listening. I thank Davidron that I have been invited as a presenter, and I hope you understood everything. And if you have questions, you can write it to Davidron, to Ibiza. He can forward it to me or answer it himself. And if you have commercial question about, please get in contact with Davidron.
Yeah. So
thank you.
Horst, again, thank you so much. It was very interesting. Of course, the videos at the end as well to show the accuracy of those high precision current measurement sensors. I have no questions, so nobody asked. So your English must have been very good, and you explained everything.
Nobody understood it. Okay.
No, I think it's the thing that I said, because it was really, really good. And thank you so much again. And to all the listeners, thank you for taking part. Cheers. And if you have any further questions, feel free to contact me or my colleagues, and we are going to get in contact with Horst if necessary. Thank you so much. Bye-bye, and have a good day.
And goodbye. Thank you. Bye.
If you have any further questions, feel free to contact me or my colleagues.